Tom Nowick. He is our engineer focusing on radiating cables product line. He's going to be getting into the meat and potatoes of our presentation. We'll be educating you on our radiating cable line. Yeah, go ahead, Tom. Thanks. So a little bit about Eupen Cable is, Eupen was founded in 1747. We've been around a while. We've been through quite a few things, I would say, since the 1700s, and we're still standing and making cable. We are a privately owned company by the Berceau family, and we are still owned by the Berceau family to this day. Mr. Berceau comes into the office, 90-year-old man with his little cute little suit on, and interacts with everybody. To the right is a picture of our factory, and that is actually the entire town of Eupen, Belgium. And we employ most of the population of Eupen. And we landed here in the US about 25 years ago, and that's where our corporate headquarters are to this day, are in Tampa, Florida. Thank you. So these Eupen Cable manufactures about 30,000 different cables. We've been doing this for a long time. These are just some of the quick overview of things that we do. Power generation, utilities, oil and gas, chemical, industrial, telecoms, airfield lighting, rail and light, and green energy. This is just a quick overview of our history. I'm just gonna go through and point out the important dates. Like in 1972 is when we started production of the RF cables. Prior to that, in the 1700s, we were making jute rope for sail ships. And then in 1993, we became ISO certified. This is a big one. 1994, we began specifying PIM for cables and connectors far before the United States did. 2011, we started 100% testing all of our factory RF jumpers for PIM. And in 2012, we launched our hybrid cable solutions, and here today we are optimizing our cables to perform up to 6 gigahertz for the CBRS and those lower bands. This is just a brief overview of what we focus here in the US. We focus only on the 50 ohm cables. We have your traditional coax, foam coax outdoor rated cabling in all sizes. We have elliptical waveguide that we manufacture. We also manufacture our connectors as well. We have a line of plenum rated cabling in several different colors, your traditional blue and white. And then we have red, black, and gray is soon to be in our warehouse. We custom make jumpers, 100% tested, any size, any connector configuration you desire. We also have a 1/4 inch high flex plenum rated cable for plenum jumpers. And then of course our hybrid fiber solutions with power and fiber inside the cables. And then what Tom is going to be educating you on today is our radiating cable product line. Without further ado, I give you Tom.
Thank you, Tracy. Hello, everybody. As she said, my name is Tom Nowick. I've been working in the RF industry for roughly 20 years now. Basically, most of my 20 years. A few years I went away, but I came back. Apparently, I missed it too much, so I had to come back. And I am a business development engineer for Eupen, focusing on the radiating cable line right now. So today's presentation, I'm going to talk about really what is radiating cable, where it's used, how does it work, how do we test the cable, some of the advantages of the Eupen cable that we produce, and if we have some time, some case studies and questions and review at the end. So the presentation is going to be mostly on how the product actually works and how we use the product in real life applications. So starting off, what is radiating cable? Radiating cable has quite a few names. The common name that is out there is typically leaky feeder cable. So essentially what we're doing is we're taking our standard coaxial cable that we know has an input and an output, but now we're putting a slot that has been specifically placed along the outer conductor that will allow a signal to travel in and out of the cable. So what we're doing is taking our coaxial cable and we're turning it into a very long antenna is what we're doing. So we have basically a 2-in-1, our coax and antenna in one product. So coaxial cables are inherently broad-banded, so we can cover multiple frequency lengths, and they are a passive device. So that means there's no active devices in them. They will not create a spark, and you can put them in hazardous areas. Being a coaxial cable, of course, very low maintenance, so total cost of ownership is very low once you install the cable. Being broad-banded, typically you don't have to touch it, just maintain it. As long as it's maintained well, you can change the technologies or the frequencies going into it. So total cost of ownership tends to be very low, and there's a very long mean time between failures when it comes to these cables. Where do we use these cables and why would we use them? So we use them in many different areas. Listed here on the slide: transportation, industrial, in building, and there's all different areas within those 3 different topics. So one thing you're going to notice is based off all the pictures below is really you're seeing a lot of areas that are confined, tunnels, metros, and these areas are very optimal for radiating cable because of the way that they work. As mentioned before, we created a very long antenna, and this is optimal for these environments. So diving in a little bit deeper to transportation, as you can see on the slide, there are multiple frequency ranges being used: VHF, UHF, GSM 900, all the way up to LTE bands and 5G. So what we're saying here is these cables being broad-banded, they can work in any frequency range that you can use today. The cables can work at those frequencies. So for telecom or emergency services or whatever it might be, especially in confined environments, it's optimal for those areas. The logistical, production, construction, and mining, a lot of where it could be used within these industries tends to be revolving around RFID tags, but it can be more than that. It can also be your communication services for public safety or VHF, UHF, personal communication. Along with point source antennas, we can use our cables to cover these areas for, as in factories and or mines in construction for small confined areas. In building is another area where the cables can be used. Now, typically in building, you think of more of an open space and say a DAS system. A distributed antenna system are typically used in these areas, but not all areas of building can use an antenna because you might have somewhere like an elevator shaft or an underground basement tunnel that has concrete or rebar where the point source antennas, once you go around a corner, you lose the signal. You can use the radiating cables in these areas. So radiating cable tends to be used in conjunction with the DAS systems, typically in a lot of these bigger venues. So we start to talk now about the 2 types of radiating cable that exist. There's a coupled mode and there's a radiating mode. Coupled mode is relatively simple. We take something like our basic corrugated cable and we just mill off the top of the corrugations before we jacket it. What we're doing now is just allowing the signal to couple out of the cable and go into the air. So we're not controlling it that much, we're just letting it go. The same with this smooth wall type cable, we're just going to put a long longitudinal slot right down the cable, allowing the signal to leak out. So it's not really controlled or designed to go in any type of pattern, it's just coming off of the cable as it would with a hole in it. The other type is called a radiating mode. This one is a little more complicated. Now, radiating mode cables are smooth wall cables only because on corrugated cables, you cannot create patterns within the corrugations because of just the design of the cable, the peaks and the valleys. So smooth wall only, and what we're doing with these is we're actually placing precision placed holes along the outer conductor to create a pattern. Similar to like you would do with dipoles in an antenna, we're creating a pattern here and we're radiating the signal off of the cable. And being cable, it is still broadband, and we can actually tune these cables with these patterns. So how does the cable work? As we've mentioned already, we are basically adding holes or slots to the cable. So the electric signal is already coming down the cable. You have your input and your output, and as the signal's coming down the cable, we're allowing it to leak out of the cable. So when we place these holes or design these holes and pattern or slots into the outer conductor, we're actually looking at it like an antenna. Like when you have a half wavelength dipole antenna, you will stack those dipoles to create a pattern or put them side by side depending on how you're building your antenna. We're doing the same with a cable. We're actually putting slots into the cable to optimize our patterns or the performance of the signal coming off of the cable. We're treating it like dipoles. In a typical radiating cable, you're going to see there's intervals of slots and then no slots, a smooth area and then slots again. So we're treating those like individual dipoles, creating essentially, as we said before, a very long antenna. Why would you even want to use a radiating cable, or what is the reason behind radiating alpha cable? So antennas are very easy to use and they cover a very wide area, very broad area typically. That's great when you have open space and you have line of sight to these antennas. But as mentioned before, confined areas, tunnels, mining, where you start turning corners. Every time you turn a corner with these materials, these rocks or these rebar and concrete, you lose your signal. You have to put another antenna, then another antenna. So you're constantly cutting into the main line running to jump off to an antenna. So as you do this, you're adding more potentials for PIM and just adding more losses to your system, where running a radiating cable can do the same thing around these corners and around bends, giving you a very consistent signal. And what you're really looking for is your longitudinal loss, your input power to your output power, and your coupling loss added on top of it to give you a very consistent pattern. And when your coupling loss or your overall losses get low enough, you can just boost it again with a BDA and bring the signal back up and keep the signal running consistently throughout your area that you want to cover. And how do the cables work? Well, I wouldn't say very complicated, but there's enough black magic behind it. Our engineers are actually working to develop patterns into the cable. As mentioned before, there's intervals of slots and then no slots. In those intervals, we actually have to design these slots to work for the frequencies that we want to cover. And also we want to design it so it has consistent uniform pattern all the way down the cable. So no matter where you are, you can figure out your link budget by your longitudinal loss added to your coupling loss. So there's some HFSS analytics that are going on here when we look at this, and there's also calculations, but simply put, they've done all this work and they figured out what the optimal hole sizes and spacing should be in order to create these even patterns going down the cable. So as you create a link budget, you know exactly what you should see at the cable at that certain length. How do we test the cables? So when you test radiating cables, there is two values you typically look for. The first value is going to be your longitudinal loss, as we know from any basic coaxial cable, your input to your output, how much power you lose in the cable run itself. And then we have a second spec that is called our coupling loss. This is the actual value of the RF signal leaking off the cable. So from that point in the cable, you figure out your longitudinal loss, then you add your coupling loss to see how much more power you've lost at that point. And it's usually measured, or it is measured, at 2 meters away from the cable. And there is a specific test defined by IEC 61196-4 that will tell you how you're to measure these values. And really what it is on the bottom we show a picture. There is a cart there. In that cart you have a network analyzer going up to an antenna on the top. The antenna is 2 meters away from the cable that are mounted on these poles in free space. We inject the known signal into the cable, and the antenna is then reading the output of that cable along this mini rail or railroad track that the cart is running down. Now there are 3 different antennas up top, an orthogonal, and a radial, and a parallel antenna. So we take 3 different measurements. Then at the end of it, we average them all together and come up with one average coupling loss value. So that is the typical free space method that is used to test radiating cables, and all manufacturers use that method. The specs now that it creates, there are coupling losses, as we said. That's the most important spec when it comes to radiating cable. That's telling you how much strength or how strong the signal is coming out of that cable at that point, how much loss it has at 2 meters away, so you can determine your link budget for your end user. Usually the coupling losses are defined with 2 values. There's a 50% value and a 95% value. And what we're trying to state here is, if you look at the bottom left-hand graph, as you read your measurements coming out, the top is going to be the power inside the cable, the dotted yellow line, and you go down, there's 100% range you're going to read, but 50% of the time you're looking at a value that's within that upper part of the graph, which is usually a better coupling loss value. Then there's a 95% value that you see farther down below that's going to be a little bit worse. So the 95% value is more realistic, which means if you're using that 95% value, usually you're going to see that coupling loss, if not better, at that point in the cable. So it's a good estimate for your link budget. To the right, this is just a simple graph. It's not 100% accurate, but just telling you typically, with your power on the left of the graph, the length on the bottom, your longitudinal loss of your cable will increase as you get longer. When you add your coupling loss, which is consistent, you should then have a total power budget coming out to the receiver of the bottom line below. So really, your longitudinal loss with your coupling losses added give you what your receiver strength should be at 2 meters from the cable when you do your link budget. So testing in tunnels in free field. There are 2 ways to test the cable. The free space method we just talked about, that is defined by the IEC. That is a good method, but the reality is, who's going to use radiating cable in free space? It is usually used in tunnels and confined areas. So now when you put the cables closer to the wall or any type of material, it's going to have a reaction with the cable. It's going to affect the overall performance. So what Eupen has done for many years is we actually, as a company, had the ability to test our cables against the wall in a tunnel in a real life environment. Fun story, many years in the past, Belgium decided to actually make a subway system throughout their country. But for political reasons, they never finished it. So they built these tunnels, but never actually physically built the subway in there. So these tunnels were existing around Belgium with no use and nothing happening to them. One of them was about 30 minutes away from our plant in Belgium. So they asked the government to use this tunnel, and they allowed them to use this tunnel for many years to actually mount the cable next to tunnel walls and take real life data and do all the testing they needed in order to get the information they needed. So we would, this was one method we'd had for many years, and it was actually great because not always can you find a tunnel long enough to test this product and get really good data. So this was always unique to Eupen. We've always had this ability to use these tunnels and get this good data if a customer ever asked us, or if we had to do some more testing or advanced testing. Bad news was, about 3-4 years ago, the government shut down these tunnels. After years of no use and no maintenance, they finally deemed them unusable and unsafe for people. So they shut them down, which is hard for us to take, but in turn, we turned around and built our own makeshift tunnel in the back of our facility because we know the benefits of having real life testing. So we built one. This is in the back of our Eupen facility in Belgium. There's a right-hand picture. You see the free space method, the tracks, and then the poles that mount the cable. And right behind it is our makeshift tunnel. The left-hand picture is actually inside the tunnel. We put more tracks in there. And you can see how the cable is mounted near the wall. So a real-life metro situation, we can take data based off your scenario, take measurements, and tell you what you would expect to see with the cables mounted against the wall. Now, why am I stressing this? Why is this important? As said before, that's how you're going to use the cables. They are typically mounted against something, and mounting against the wall has an effect. It has effect on the longitudinal loss and the coupling loss. So if you read a data sheet and you only see free space data, that's great. But as it gets closer to the wall, that data is going to gradually get worse. The longitudinal loss will increase, and so will the coupling loss. So if you want to see what you're really going to get, you want to mount the cable near the wall. And all of the data sheets that Eupen post has the values of the cables mounted near the wall. It's called the ground level method. So we're testing it the same way, 3 different polarizations of the antenna running down the track 2 meters away from the cable, but now it's actually mounted near the wall like you would actually apply it in a real life situation. And this means now when you go to test your system in the field after it is installed, the coupling losses that you read from our data sheet should be very close to what you're reading now in that system. So that is unique for us, and no one else does actually post their spec that way. A few more advantages of our cable that make it slightly different is, well, starting off, we know PIM is a big subject out there in the field. So everybody is worried about PIM because PIM is in your system, especially at higher frequencies. It starts to affect your performance and your data rates. So looking at our cables, cables by themselves are inherently PIM free. They are one continuous piece and there is really no PIM in it. But how do you know that? Because you have to put connectors on to read it. As you start to add mismatches, as in connectors to get to an interface, that's where the PIM is now generated, in that mismatch. So with our connectors attached to our cable, we're looking typically at a PIM rating of 163.8 dBc. This is very stable PIM, and this is as long as there's no kind of interference around it, magnetic parts, smartphones, metallic parts, anything that could interfere in the signal could generate PIM. But by itself, with the connectors on and nothing interfering, it's a very PIM stable cable, just like the standard corrugated cable you would use. The connectors are a big part of keeping PIM stable, and Eupen has developed their own connectors to go on our cable that are very PIM stable. We spec it at 155 dBc, but typically you're going to see around 163 dBc. This is in both static and dynamic conditions. There are multiple interfaces that can be offered. 4.3-10 is very common for the higher frequencies. Lower frequencies, we still have 7/16 DIN and N types that are available. And another unique thing about these connectors is when they are installed, they are watertight. They're IP67 or 68 rated. They are easy to install with the right tools, maybe 1 to 2 minutes to get a connector on, but once the back nut is tightened down to the body, you do have a watertight connector, no need for a heat shrink boot. So once it's on and tightened, it is complete. Now the cable itself, we talked a little while back about the slots and the patterns in the cable and how you can generate different patterns. So every company has their patented design that they use, and Eupen, like everybody else, came up with our own patented technology based off how we want to radiate the signal off the cable. So knowing the cables are broad banded, they can go up to 6 gigahertz. Of course, cables allowing to go to those frequencies. There are cutoff frequencies based off size. For example, 1 5/8 inch, you have to cut off at 2.7 gigahertz, so you cannot use it at 6. Half inch can be used at 6. So just knowing this, we looked at the cables and Eupen said, how do we make our cables, what is it that makes our cables really work better than everyone else's? So as we looked at how typically radiating cables are designed, you want to shoot the signal straight off the cable. Looking at the top picture, that's a standard design. You have your interval slots, no slots, interval slots, and as you go down the cable and you read your signal strength, there's going to be areas where it's stronger and a little bit weaker between the slots, and then stronger and weaker. So you get this fading in and out of the pattern. That is the standard way to radiate your signal. So Eupen did a lot of work and realized at one point, if I take my signal and I just start to fade it to the right, what that does is now the field densities start to build up as you start to push one signal over on the next one. You can see how the other signal is starting to push up on it, but you start to create this pattern that actually becomes very stable. There's very minimal fading when you actually push that signal to the right. So even though there are intervals of slots in between these signals, now my fading is very minimal. And also, with the way the field densities have built up in this pattern, you also have achieved about 10 dB better coupling losses on average than coming straight off of the cable. So you've created a cable with a very stable fading and also much less coupling loss on average than coming straight off the cable. That is a patented design by Eupen, and we are the only ones that have our signal coming off the cable in this way. As mentioned earlier, we can tune our cables. So we know that even with dipoles and antennas, to have a very broadband dipole, there's always a limitation somewhere. Something's going to suffer because of the broadband nature. So we can make broadband cable, but we also can take our cables and tune them, going back to the size of the slot, the spacing between the slots, and where we want to optimize the cable to. We've actually created multiple areas where the cables are optimized for performance. For example, if you're working down in VHF, UHF frequencies, there's a T-type or tetra cable that is optimized for better coupling loss in lower frequencies than the higher ones, or vice versa. You go to 5G, LTE, WLAN, you want better performance up there because you're not working in lower frequencies. We have cables that are optimized for those frequencies. So we do offer all these different types of cable today. If you know where you're working and want optimal performance, we can pick the right cable for your application. A few more, here's an example actually of the cable performance itself. So I just want to give a quick example. I'm looking at the 95% coupling loss value of our T-type or tetra cable, focusing lower frequencies. Left-hand side of the chart, your dB value. Bottom of the chart is your frequencies, 150 to 925 megahertz. So you can see the coupling loss values range from, say, 70 down to almost low 50s and goes back up. So optimized around 450 megahertz. So lower coupling losses at the lower frequencies in that band. The second chart is longitudinal losses. So your cable, as you start to lose, as the frequencies go up, your longitudinal losses get higher. You combine the two, your coupling loss and longitudinal, you should see a value right here to the left again. You have your dB scale and your frequencies at the bottom. A very stable performance at the lower frequencies. So you have a consistent pattern coming off of the cable. But at the higher frequencies, if you're not using that band, we don't care about what's happening there because you're not using it, but it gets much higher. Vice versa, you're using the upper frequencies and not the lower. Here's an example of focusing around the 900 megahertz area, GSM. So the 900 coupling loss, 95%, sitting around 75 dB, a little bit lower. So consistent at the higher frequencies. The lower ones, you see how they jump up a little bit. Add your longitudinal loss, which will increase with lengths, and combine the two for a system loss. Very consistent at the upper frequencies. Now you have much lower loss in the low to mid 70s versus the lower frequencies that jump up a little bit. So depending on where you're working, we can pick the right cable to be optimized for your frequency. A few additional features of our cable is when we get to this point, CBRS is becoming a very hot topic. Everyone's starting to talk about it. It's not being used yet, but if it does come up and people start to use this band, we now have a product that is ready to be used in this band. Typically in the past, a lot of cables like 1 5/8 will cut off at 2.7 gigahertz, and a lot of the 1 1/4 cables also cut off at 2.7. But our cables always went higher than that. So in our case, our 1 1/4 can go to 3.8 gigahertz. So we are ready for CBRS when the end users get to use that signal. And also, we do support MIMO applications with this cable. And this is becoming another topic of discussion. Typically, when you want to add MIMO, multi-input, multi-output, a 2x2 MIMO, standard applications require you to use 2 different cables, usually with 2 different orientations coming off the cable, like a horizontal and vertical polarization, to try to give you that multipathing and fading in the tunnel environments to get that MIMO signal and high bit rates. Going back to how Eupen cables have that 45-degree pattern coming off of it, if you can actually take your radios, put one at each end of the cable, say with a fiber optic connection in between, and you push the signal down both sides of the cable towards each other, the signal coming down from the other side will go in a minus 45-degree pattern, which in a sense creates a cross-pole antenna, or 2 different polarizations on one cable. So this is an option if you're going down the MIMO path, where we can do 2x2 MIMO on 1 cable versus 2 cable, or if you go to 4x4 MIMO, that's 2 cables versus 1. So if there's interest, we can always talk about this in future meetings. So that pretty much covers what we have to talk about today on radiating cables. There's just a few case studies we have done in the past. I'll just go over some of them quickly just to kind of show you what we have done and where we have worked in the past. So in the US, we have done quite a few projects, but we have done more projects overseas in Europe where Belgium or Eupen is located. So for example, these tunnels in Sweden, we have done a lot of them up in that area. We are one of their preferred suppliers, so almost every tunnel and metro done in the area has our cable in it. So we've been doing these systems for many years, and we have a lot of experience within these tunnel systems throughout Europe. The same goes with the SBK Smart Line. This is another system we helped to put in. So about, I think there was 9.5 kilometers of this cable underground, but the total system was about 51 kilometers. So we've done this whole system with the MRT Corp. And this smart line was also where we did some testing on our MIMO capabilities with our cables. We tested both 2 cables and 1 cable to see how they would perform in these tunnel situations. We have a lot of data on it to prove that our 1 cable can work just as good as 2 cables. So it was a very unique project and very advanced project with multiple frequencies being used in this system today. This is a tunnel in Kuala Lumpur. It's a very unique tunnel. This is a long video. I'm not going to play. It's about 4 minutes long, but the story behind it is Kuala Lumpur wanted to create a tunnel to help minimize flooding during the rainy season. So they created this tunnel, but say 3/4 of the year, it wouldn't be used because it wasn't flooding. And that flooding caused a lot of damage. So you decided to take this tunnel, make it dual purpose. Along with draining all the floodwaters out, it would also serve as a 2-level highway. So they created this full tunnel as a 2-level highway, and during flood seasons, they would open the gates and allow the floodwaters to run through it. But when the flood seasons were over, they would close the gates and use it as a 2-level highway to minimize congestion in the traffic in the city. So that helped a lot minimizing congestion. But our cables are in this system, and actually it tells you they go underwater every year during flood season. And when the tunnel empties back out, they turn the system back on and good to go. So it's a very unique project. It took about, I think, 8 or 10 years to complete. So it was a unique project and a lot of mining. Office building applications, a lot of times DAS systems are here, but radiating cable can be used in this type of situation. You have 1 floor, you're covering 1 floor in the office building. You can run a cable down the middle near the ceiling and then cover multiple offices and areas with that 1 cable. So it is an application that we can do with these cables if point source antennas are not able to be used. You can also hide radiating cable much better than you can a point source antenna. We've done many baggage sorting systems throughout the world. So a lot of the systems in airports in the US and in Europe have these sorting systems, and a lot of them may actually have our radiating cable within these systems, along with the tram systems that actually bring these carts back and forth in the airports. So we have radiating cables in multiple airports around the world doing RFID and also kind of running the trams that go through the system or the airports. Warehousing, going back to RFID, tracking either where the forklift could be or the product is within the warehouse. We have run cables in multiple areas covering a lot of warehouses throughout the Europe and in the US. Just an example of how we can run some of our cable down the main hallways, up and down where the products are, depending on where you want to cover and what you want to cover, we can run the cables in these areas. So that covers the presentation that I had for today.
All right, that's a great presentation, Tracy and Tom. I like how you break down the details specific, like the